Okay, I'm recording now. Yeah. Another thing is that I will also share in the Zoom chat the link to my website with the workshops, where you can find information about our next workshops. So, for example, next week we'll have a workshop on uh basically data visualization with GG Animate in R. And then we have workshop on DevOps for data scientists. Then we have again another workshop on data visualization in R, and so on. You can check the full schedule on the website, and if you're interested for one of the workshops, you can register for that as well. Other than that, if no one has any pressing questions at the moment, or technical issues, or anything like that, I think we can start. So if you have any questions throughout throughout the workshop, feel free to write them in the chat. Um, and if you have also like some technical issues with Zoom, you can also write them in the chat. So yeah, I think this is all from my side. So yeah, I don't think anyone has any questions, so I will give the floor to Adam, who will be our today's speaker. Thank you a lot.
Thank you, Daria. So I will start by sharing my screen first. All right. So the first thing I should begin by saying that it's an honor to be presenting here, and supporting Ukraine in this difficult time means a lot to me. I'm very happy to be contributing in this workshop, and I truly hope that all Ukrainians can live safely in their homes soon. So yeah. So let's begin. So the topic today for my presentation is Introduction to Empirical Macroeconomics with R. And my real Chinese name is Wang Xiaolei, and my fake English name is Adam. And I enjoy using my fake name, so you can please call me Adam. So during any time during the workshop, you can just unmute yourself or type in the chat to ask me any questions. All right, so something about me first. So I am a third-year PhD student at the University of Melbourne, major in economics, and my research topic is mainly on Bayesian econometrics. So which is what this R package is about. So I'm the author of this R package, piece for science, and we will be mainly working with this package in this workshop. So so this is the logo of my package, and I think halfway through this workshop, you have an idea of what this figure means. So you can look forward to that. And so the plan for today, so we have three main sections. First is I will talk about the vector autoregression model, which is the basis of the next main section, structural vector autoregression models. So the vector autoregression model is a forecasting model, and building on the forecasting model, these structural vector autoregression models will allow us to make causal inferences with this building on the vector autoregression model. And finally, I will finish with a application in macroeconomics. And also throughout the workshop, we will have many fun exercises in R. All right, so some prerequisites for this workshop, you should install this package I just mentioned, BizFar Science. You can do this just by typing install.packages and double quotation BizFar Science in RStudio. And also you also need to install the read Excel package to read an Excel file that I provided. So I think I missed this prerequisite. But you can do this later. And you also need to download some files from this link, which is also provided as a zip file, I think. So if you click this link, it will bring you to a GitHub repo. And it contains many exercise files and also a dataset. So you need to download these files for this workshop. But don't worry, I will show you the exact steps when we go to the exercises. Okay. So if you have any questions, or you can just type in the chat or just unmute yourself. All right, so let's begin with the first section, vector autoregression. So the vector autoregression, or in the the short term is VAR or VAR. A VAR model is a system of equations where each variable is regressed on its own lag values and the lag values of all other variables. For example, if we consider this bivariate var1, which means we only have two variables in this var model, and the one here indicates that we only include one lag. So in this model, we have two variables and one lag. So you see the t minus 1 here. It indicates that we only include one lag. And this model will allow us to model the linear dynamic interdependencies. For example, A1, comma 1, 1 entry will tell us how y1 t minus 1 affect y1 t, and A1, comma 1, 2 will tell us how y2 t minus 1 affect y1 t. And similarly for A1, comma 2, 1, A1, comma 2, 2. And we also assume this error term will append at the end to follow a normal distribution. And since we have two variables here, so it will be also a bivariate normal. And it is assumed to have zero mean and a covariance matrix that is 2 by 2. Because we have two variables, so the covariance matrix will be 2 by 2. And the covariance matrix will have entries sigma 1, 1, sigma 1, 2. You can write this as sigma 2, 1, but a covariance matrix is symmetric, so flipping the matrix does not change anything. So this entry sigma 2, 1 is the same as sigma 1, 2. So to emphasize the symmetry of this matrix, I will just write sigma 1, 2 here. And also at the end, we have sigma 2, 2 in the bottom right corner. So, however, if we always write this var model explicitly, it can include many variables and many coefficients. So things can get messy very soon. So I will introduce this matrix notation. If we collect this y1t and y2t together with a vector yt, so this yt will be a column vector containing y1t and y2t. And this A1 matrix will contain these four entries, A1, 1, 1, A1, 1, 2, etc. And YT minus 1, similar to YT, will contain Y1 T minus 1 and Y2 T minus 1. And also this epsilon T vector of errors will contain epsilon 1T and epsilon 2T. And similarly, we can also write the distribution of the error term in the matrix notation. It will follow a normal distribution with zero mean and a covariance matrix sigma. So this vector autoregression model is useful for forecasting. For example, if you look at this equation here, if we want to forecast at a period yt plus 1, then we can just say the expectation of yt plus 1 will be equal to a1 times yt, because we can always propagate this equation forward. So this model is useful for forecasting, and we can also test for something called the Granger causality here. So the Granger causality simply is testing whether the lag of the other variable cause another variable. So for example, here we can test whether the lag of y2 will sorry, I think I made a mistake. So the Granger causality means whether the lag of one variable can be used to predict another variable. For example, here we can test whether the lag of y2 has a predictive power to y1t. So here the entry A1, 1, 2 will capture this effect, because if we multiply this A1 and yt minus 1 matrix, you will see that A1, 1, 2 will be used to multiply with y2 t minus 1. So we can test whether this coefficient is significantly different from 0 or not. So if it is significantly different from 0, then we say y2 Granger causes y1 because the lag of y2 has some predictive power to y1. And if it is not significantly different from 0, then we say y2 does not Granger cause y1. So the VAR model, so in summary, the VAR model is useful for forecasting and testing for whether one variable can be used to predict another. However, this does not allow us to make things that to really make some causal statements. So the causal Granger causality here does not actually mean causality. All right, so in the previous slide, we introduced the var1 model. However, in practice, we usually work with some var-p model. So we want to include more lags instead of just one lag, because that will probably make our prediction better. And so if we can write this var-p model in a matrix form, so this can be written as yt equals to a1, yt minus 1. So this part is the same as the in the previous slide as the var1 model. But here we also include a2, yt minus 2, and then other, for example, a3, yt minus 3, a4, yt minus 4, etc. Until ap, yt minus p. So we in total, we include p lags here. And for completeness, we also include this AD dt term at the end. And this dt term will contain some exogenous variables, which means things that are not simultaneously causing each other with yt. And one example would be the constant term. So the dt can be a vector, column vector of ones. So they will just be constants. So obviously the constant will not be simultaneously affecting yt or the other variables. And similarly, we also have this error term at the end, epsilon t. So we can even write this from more compactly. So if we can transform this equation into the next equation here. So if we collect all these coefficients, a1, a2, etc., up to ap in a very big matrix. So if we stack them horizontally, so a1, a2, etc., ap, and then also ad. And then we also stack these vectors of variables yt. So together, so we have yt minus 1, yt minus 2, up to yt minus p, and also the dt, the exogenous variables at the end. So if you try to multiply these two matrices, you will see we will get this first equation back, because a1 will be multiplied with at minus 1, etc. And ap will be multiplied by at minus p, and ad will be multiplied by dt. And we can even write this equation more compactly. So I will introduce this matrix A. So matrix A here will be equivalent to this very big matrix that contains all the A1 to AP and AD. And also this xt vector. So this will be a super long vector that contains all these yt minus 1 to yt minus p, and also dt at the end. And also similarly for the error term is still a normal distribution with zero mean and covariance sigma. All right, so that's all for the notations of the setup of the VAR model. So since I'm interested in Bayesian econometrics, so I will talk about the Bayesian estimation of this model. So the goal here is that in the VAR model, we want to estimate this coefficient matrix A and the covariance of the error term sigma here. So the goal is to estimate A and sigma. So in the simplest term, so there's something called a conjugate prior, which means if we place this prior on A and sigma, then the posterior given data of these parameters, they will also have the same distributions. So for example, here, if we specify that A given sigma follows a matrix normal distribution, I will introduce what matrix normal distribution later. So if we assume A given sigma follows a matrix normal distribution, and sigma follows a inverse Richard distribution, whatever that means, and I will introduce them later. So if we assume these two things to be true, then this can give us a closed form posterior distributions. So then A given sigma and data will also follow this matrix normal, which is the same as the prior. So both of them have this matrix normal distribution. And also the covariance matrix sigma given data will still follow this inverse Richard distribution, although the parameters within this distribution will be different. For example, here the mean was A underscore, but here we have a upper bar. So although the parameters within the distributions change, the actual distribution is still the same. So now what's the matrix normal distribution? So the matrix normal distribution is just a notation for a matrix that is follows a normal distribution. And the definition is that if we vectorize A here, so if we stack all the columns of A together and convert this very big matrix A into a super long column vector, then this super long column vector will follow this normal distribution, where the mean is the vectorized M of the matrix normal mean, and also the covariance will be V Kronecker U. So this circle cross product will means the Kronecker product. Although you don't need to know the details of how Kronecker product works, this is just for completeness. I'm showing you the definition. And the IW distribution is called the inverse Richard distribution. So in short, so this distribution is for positive definite matrices, and that's what covariance matrices are. So covariance matrices are positive definite matrices. So naturally, this inverse Richard distribution is a very good choice for covariance matrices. And this is also a generalization of the inverse gamma distribution. So inverse gamma in univariate linear regression, inverse gamma is always or commonly used for the variance sigma square. Here, the inverse Richard is just a multivariate generalization of the inverse gamma distribution. So they can be used to model a univariate covariance matrix. All right, so since we have talked about the how do we do the Bayesian estimation of this model? However, in this last slide, we still have this mysterious term or the parameter or the hyperparameters A underscore, V underscore, S underscore, and nu underscore. So we still don't need to how to specify these hyperparameters. So one way to specify these hyperparameters is called Minnesota prior, which is developed by people from the Minnesota University. And so how this prior works is that they set the non-stationary variables, they will set the corresponding elements in A to 1, which means in A underscore to 1, which means the mean will just be 1. And if you go back to to make this more clear, we can go back a few slides. So if we fix the prior of this element A1, 1, to 1, then this tells us that this suggests that this Y1t variable is non-stationary because this coefficient is 1. And second, for V underscore here, we want to shrink distant lag coefficient to 0 with some small values in this matrix. To be clear, this matrix is also diagonal. So everything outside the diagonal will be 0. And only things on the diagonal will have some values. And for more distant lags, the value will be smaller. So which means that we want to shrink further lags of the coefficients to closer to 0. And the benefit of doing this is that we will improve the forecasting performance by reduce overfitting. And also for completeness, for the S underscore and new underscore, I will set them to be the identity matrix and new underscore to be n plus 2. So n here is the number of variables. For example, in the bivariate model, it would just be 2. So now we can talk about an example that is used in the package. So if we call library bsparscience, so if we load the package, then this dataset optimism is automatically loaded in from the package. And this is a preview of the dataset optimism. So this dataset contains 5 quarterly US data from 1955 quarter 1 to 2010 quarter 4. And it has 5 variables. The first is the productivity that's available online here. So this first column here is a measure of how productive people in the US is. And the second variable is the stock prices. It is taken to be the S&P 500 index. I think it is the end of period S&P 500 index divided by the consumer price index. But you see there are some negative numbers here, which is strange. That's because we take the log of these variables. So you will see some negative numbers here. And the third variable is consumption, so which stands for the real consumption expenditures. And you also see these negative numbers because we take the log of this variable. And also we have the fourth variable is the real interest rate, which is defined as the federal funds rate minus inflation. So the federal funds rate is the policy rate in the US, which is set by the Federal Reserve Bank. And the final variable is hours worked. So it is defined as how many hours do people work in the non-farm industry sector. And you see these negative numbers because we took the log of this variable. So for nerdy people like me, there are 2 references of this data set. So you can take a look at this paper if you are interested. So having introduced this dataset, we can do some analysis with this. So first, we just want to do forecast since we just introduced the VAR model and it is good for forecasting. So to make a forecast with this variable, we just need to run 2 lines of code with our package bsvar science. So the first line, if you ignore the sassy here, so the first line is creating a specification object that's done by calling this specify bsvar sign $new. So this $new will create an object. And the first input in this method is the optimism dataset. And we also specify the number of legs P to be 4. And the second line of code will be creating this posterior object. And we just need to call the estimate function or method, and put in the specification object as the first argument. And then also this capital S here. So the capital S here is the number of draws or samples you want to have. And here I will just use 5,000. So that is pretty large. So you can see it can be easily done to estimate this bar model. It can be easily done with this package. You only need to type 2 lines of code, and you can copy paste this and address if you want to apply this to another data set. So you just need to change optimism here to any other data set you are using. So after fitting the var model, you can do 2 things. The first is show the fitted values. And to do this is also very simple. You just need to compute the fitted values first. So you can assign fit to this function compute fitted values and then put in the posterior object as the first argument. So this will generate the fitted values object. And you can plot these fitted values using the command plot. And this will show you how the fitted values look like. And this will be variable 1, variable 2, 3, 4, and 5. So you can see the fitted values are pretty close to the actual data, which indicates that the VAR model is doing a good job. And second, we can do the actual forecast. So again, it's very simple to do the forecast with this package. You just need to run 2 lines of code. The first is, again, assign a forecast object to this forecast function and put in the posterior object as the first argument and specify the horizon you want to forecast. For example, here I will specify it to be 4. So we want to forecast 4 periods ahead. So this will be 4 periods here. And then we can plot the forecasted values. And the second argument here, data we plot here is just how many data you want to show in this plot. So here I put 0.2 or 20% here to make the plot more zooming at the end of the period, at the end of data set. If I don't make this, if I don't include this argument, or if I put a 1 here, then you can imagine this, we have a lot of data, and just in the end, we have a small section of the forecast, so it will not be very informative. So adjusting this parameter can show a more informative plot at the near the end of the period. All right, so that's all for the vector autoregression section, and we should move on to the first exercise. So you can all try to estimate this bar model and run this exercise. So the exercise will be about plotting the fitted values and the forecast values using very similar commands here I show you. So to do this, you just need to download the exercise1.r file and just run the whole script, and then it will plot the fitted values and forecasts. So I will show you how to do this. If you don't have the zip files yet, I will show you how to download it online. So you can go to the GitHub repo here. I will send this in chat. So the easiest way to do this is just click code here and then download zip. And then you can see it is downloading the whole GitHub repo. By the way, you can also access the presentation slides here. And I will also send this in chat.
Hello, everyone. Can you hear me?
Yep.
So greetings from Poland. It's just thank you for a very nice presentation. I would like to ask about those fitted values with those, I think, highest density intervals. Can you comment about how we can adjust them? I'm talking about this measure of uncertainty, because we see that you plotted the fitted values with some bounds. Yes. So can you comment on that? And the same for forecasting, maybe. How can we just set the confident intervals, or let's call it highest density intervals in those two exercises?
Yeah, sure, of course. To be honest, I don't remember the syntax on the spot, but I guess we can try this. So if I load the package first, and then maybe calling the help file, I think it will show us. Unfortunately, the help file does not say how to do that. Maybe I can try to look at the code if there's
Okay,
something that says how to
we
adjust.
can skip. I just already checked that there is nothing about this inside forecast function, but okay, we can check it later on and you can move on with your presentation. Okay, I just.
Yeah, sure. Okay, thanks.
Hey, just a suggestion. There's a argument probability in the plot function, but the plot function is taken from the Bisvars package.
Oh yeah.
Mm? So if you go to if you start typing plot in your script,
Yes.
yeah, with this argument you should obtain the possibility of specifying argument probability that will contain the probability content of this intervals.
Great. Thank you for this comment. Yes, I will check that.
Yeah, so I guess if you put plot fit and then comma probability equals to some other number, it will give you a different confidence band. All right, so let's
Thanks.
move on to exercise 1. So if you downloaded the exercise folder or the whole repo, you can open this zip file and then open this whole folder and then copy this exercises folder to some place that you like. And then you can open this folder in RStudio. For example, here I place this exercises folder on my desktop. So I can open exercises on my desktop. And to run the exercise 1 file, first thing you might want to do is to set the working directory here. So you can do this by clicking more and then set as working directory. And after doing this, you can run this code here. So this will show you a progress bar that of the sampling process. And then this, if you run this script, it will show you the 2 plots. So the first plot will be the fitted values, and then the second plot will be the forecasting. So I guess if I adjust probability here with some other numbers, then we should see some different plots. Yeah. All right. So now I will give everyone 5 minutes to attempt this exercise 1, and then just to make sure that everyone has this package working, and then this you can also replicate these 2 plots of fitted values and forecasts. And maybe at the end, if you can type in the chat whether you have finished or you have run into some trouble, you can just unmute yourself or just type in the chat. So I will give you 5 minutes. So it is 35 now. So I will keep talking at 40.
We are only the only way to introduce them is via Minnesota prior specification. Yes,
Yes, that's the default.
But we
can also.
Yeah, but we can also adjust those hyperparameters here, yes, to change them from default values. Okay, I just wanted to clarify that. Thank you.
Yep. For example, you can actually address the prior here. For example, for the A matrix, you can address any element in A here. So you don't need to actually use the Minnesota prior. So you can create your own prior that does not fit in the Minnesota prior class. But by default, we just use the Minnesota prior.
Yeah, but basically your packages is based on this conjugate prior specification with shrinkage idea from Minnesota and some modification, yes, as far as I understand. Yes. Okay, great, thank you.
Yeah, thanks for the questions. All right, it's 40 now, so I will keep going, and I assume everyone can run this exercise. So good, then we can continue. And so we can move on to the next section called structural vector autoregression. So this kind of model will build from the vector autoregression models and allow us to make causal inferences. So to refresh your memory, the var equation is yt equals to a xt plus epsilon t. And A here is the super big matrix that contains all the coefficients. And xt is the super long vector that contains all the lag values of yt. So the difference between a structural var and a var is that it defines a linear relationship between epsilon t, which is the error term in the plain var model, and the structural shocks ut. So I will explain what structural shocks mean in a minute. So if we take a look at the relationship, it is ut equals to b epsilon t. So they are related by this, their linear relationship is captured by this capital B matrix. And this ut is assumed or defined to have a normal distribution with zero mean and identity matrix as the covariance. So which indicates that this u1t to unt, all these error term in the structural var model are all independent with each other and contemporaneously and also across time. So this can be interpreted as there are these u1t to unt are n distinct causal drivers. So the difference between this ut and epsilon t is that ut are n distinct causal drivers. That's the true causes of in this model. However, this epsilon t is if you look at the other equation here, if you just multiply B inverse both sides here, then epsilon t is equal to B inverse, and we define B inverse to be B0. So epsilon t is equal to B0 ut, and then you can see epsilon t is a linear combination of ut. For example, the first element in epsilon t, maybe epsilon 1t, will be equal to the first row of B0 multiplying ut. Therefore, it is a linear combination of the underlying causes. And for example, a change in epsilon t, we cannot disentangle the change in epsilon t into those n distinct causes. However, these UTs are the underlying distinct causes. So if we have a change in U1t, this effect is very clear, and we can we can make causal inferences based on these structural shocks. So the essence of the structural shocks, the reason why we define this error term ut to be structural shocks is that they are independent, and they can have the interpretation of n distinct causal drivers in this model. All right. So we can also try to look at the S-bar equation. We can treat the S-bar equation as a simultaneous equations model. So the yt is equal to, this is the var model, yt equals to a capital A xt plus epsilon t. And then yt is equal to capital A xt plus b0 ut. This is from our previous slide here. So we define b0 ut to be equal to epsilon t. And finally, in the last line, we can just multiply everything by b. So we have b1t equals to baxt, and b0 by definition is b inverse. So b multiplied by b inverse will cancel each other. So we are only left with ut. And if we skip something here and then look at the equation here, then you can see if we just look at a two variable equation, then it's clear this is a simultaneous equation model, because if you look at the first line, we have b11 pt multiplied by plus b12 multiplied by qt. So if we can also move this qt to the right hand side of the equation, and we will get these equations here. So this is a supply and demand example. So it's well known that supply and demand are determined simultaneously, or price and quantity are determined simultaneously. So if we move this B1 to QT to the right hand side here, so we have B1 to QT on the right hand side, and we also have the negative side, because this is B11 PT plus B1 to QT, and then we want to move B1 to QT to the right hand side, so we also have this negative side in the form of B12. And we can also divide B11 on both sides. So we have this equation here for the demand equation. So the demand equation is PT equals to negative B12 divided by B11 multiplied by quantity QT plus all the lag terms that we are ignoring for now, and also plus the demand shock, because this is a demand equation by our construction, since we assume B11 to be positive and B12 to be positive. So if B11 is positive and B12 is positive, the whole term here will be negative. And since demand equations have a negative slope, so this have the interpretation of a demand curve or the demand equation. And the reason why a demand equation has a negative slope is that when the price is higher, people want to buy less quantity. People want to have less quantity if the price is higher. So it has a negative slope. And similarly for the supply equation, we can also do the manipulation here. So B21 PT plus B22 QT, and then we want to move B21 PT to the right hand side. So we have negative B21 PT, and then we can also divide both sides by B22. So we have QT equals to negative B21 over B22 PT plus all the lag things we are ignoring for now, and also the supply shock. And again, here we fix B22 to be positive and B12 to be negative. So if B22 is positive and B21 is negative, then this whole thing will be positive because we have two negative things. And a positive slope will give us the interpretation of a supply curve. Because if the price is higher, then we want to supply more. So the supply equation have a positive slope. So this is so at the beginning, we introduced the general notation of a structural var model. And here we show you a very simple example of how a two-variable supply and demand equation can be modeled in these SVR notations. I think I have a small typo here. So this UT, the demand should also be divided by U1, and UST should also be divided by B22. But it doesn't change the interpretation of the slope here. And if this coefficient here also have the interpretation of something called the elasticity, if we take the log of PT and Q, the quantity and price, then this will be and have the interpretation of the elasticity, so the percentage changes. But this is a side point. So now we have introduced a notation and a simple example of the structural VAR model. I can talk about one difficult problem in estimating the structural VAR model. So it is called the identification problem. So after we feed a VAR model, and this is our notation, yt equals to A, the big matrix A, multiplying the long vector xt, and plus the epsilon t. So we want to, so after estimating this model, we have A and sigma, but without further assumptions or restrictions, we cannot recover the structural matrix B here. Because if you look at the structural VAR equation here, we have A, B, and we have the parameter we want to know is A and B. However, we only have A and sigma from after estimating a VAR model. And the problem is that B has n square elements because it's a square matrix, n by n square matrix. So it has n square elements inside this square matrix B. And sigma is, by definition, it is a covariance matrix, so it is symmetric, and it has only n multiplied by n plus 1 over 2 elements. So only the lower triangular part or the upper triangular part of a covariance matrix can be freely changed, and the other side of the diagonal have to be equal to the other side of the diagonal. So there are only n multiplied by n plus 1 over 2 elements that can be freely changed in a covariance matrix. So we actually need to impose n squared minus m times n plus 1 over 2, which is equal to n times n minus 1 over 2 restrictions or assumptions to identify this B matrix. And to repeat myself, the reason is because the number of elements in sigma is less than the number of elements in B. So to identify B, we need to impose these additional restrictions or assumptions. One popular way is to just fix B to be lower triangular. So we are forcing B to have the same number of elements as sigma. Therefore, we can identify this matrix B. However, introducing this lower triangular assumption can be very controversial. And if we go back to the supply and demand example, where we have two variables, price and quantity, if we impose this lower triangular assumption to the B matrix, then this is saying that in the demand equation, which is the first row, then in here we are saying that in the demand equation, the price does not depend on the quantity. So which is can be a very strange assumption in practice. So to fix or to relax these strong assumptions, we can consider something called sign restrictions. So first, we can introduce some restriction on the structural matrix B. So this is a less controversial way to impose to identify the matrix B, and this is called sign restrictions. For example, we know the demand curve should have a negative slope, and the supply curve should have a positive slope, which means this is because higher price will generally imply a higher quantity demanded, or a higher price will normally imply a higher quantity supply. So the demand curve is negative and the supply curve is positive. So we can use our knowledge here of the sign of the demand supply curve to identify this B matrix here. And to do this, we can normalize B11 and B22, which is these two elements, or these two elements. We can normalize them to be positive. You can choose them to be negative, but that just makes your life unnecessarily harder. So I will fix them to be positive. And then we can, again, restrict this B12 to be positive so that a negative number multiplied by a positive number will be negative. So we have a negative slope for the demand curve. And again, we can impose the B21. I think I have a hypo here, so this should be B21. So if we impose this B21 matrix to be negative, then a negative number multiplied by a negative sign will be a positive number. So this equation will have a positive slope, and this can be interpreted as the supply curve. And in the structural var notation, we can impose this restriction as follows. So if we so as I mentioned before, we want to normalize B11 and B22 to be positive. So B11 is here, it is positive, and B22 is here, and we should also make it to be positive. And next, we want to impose that B12 is positive. So we want to have B12 is positive, which is the same as saying the entry of this element in this matrix is positive. And we also want to impose that B21 is negative. So which means this element should be negative. And after imposing these restrictions, we can narrow down the posterior draws and then make some useful inference of this structural matrix B. So this brings us to the second exercise of this workshop. So we can open this exercise 2.r file, and then in this exercise we simulate some fake data in R. So we simulate some price and demand data because it contains some negative numbers, so I assume there are log price and log quantity. And this is the true model that we are simulated from. And the goal is to estimate this coefficient or the structural matrix B here by imposing some sign restrictions on this B matrix itself. And the way to do this is that we can create a sign restriction matrix. It is 2 by 2 here, so we want to create this 2 by 2 sign restriction matrix, and then put in ones where we want to impose a positive sign restriction, and put in -1 in place where we want to impose a negative restriction. And also NA for place where we want to impose any restriction. So and there's a hint to this exercise, which is the last slide here. So you just need to create this sign restriction matrix here. And then after you create this, if you run this file, then you should see that we can roughly recover this structural matrix B here. All right, so I will move to RStudio and open exercise 2. And again, I will give you 5 minutes to work on this exercise. So it is 58 now. I will keep talking at 3 past 1 in my time zone. So again, feel free to unmute yourself or type questions in the chat. So while you are working on the exercise, I can briefly talk about what this code does. So first we are setting the seed and then load the package. And then this part we are simulating the data using the true model I defined here. So these few lines of code will simulate the true data. And if you show Y here, it will give you a 1000 by 2 matrix of the variables Y we want to use. So it will contain price and quantity in this Y matrix. And then you just need to edit this part of the code and then run the following code to see whether you can recover the true structural matrix B here. So if we show the true matrix B, it will be 1 minus 1, 1, 1, which is equivalent to what we have here. So the goal here is to manipulate this line and then to make this sign restriction matrix that have the matching sign with this matrix. And after doing that, you can see running this code will help us to recover the structural matrix B.
Adam, can I ask a question about sign restriction in a Bayesian framework? Because I'm familiar with Uchlik, yes, approach to sign restriction that basically you take unitary matrix and try to rotate, let's say, B0 times U transpose B to receive different, let's say, B0 matrix, and you check, I don't know whether I express it correctly, and you check whether this new B0 matrix is good, is consistent with your sign restriction. But how it works in a Bayesian framework, because yeah, you have actually the posterior distribution of covariance matrix. So can you explain the difference between, let's say, frequency approach to this sign restriction via Uchlik and the Bayesian approach you present?
Yeah, of course. So I guess the estimation part is similar. So it's always you try to find this rotation matrix and then make the sign restrictions satisfied. So I think this is equivalent in both the frequentist and Bayesian world. The slight difference is that in Bayesian world, we have many samples, and we will need to, for all of those samples, we need to find a rotation matrix that make this particular sample satisfy the sign restrictions. But other than that, the estimation part of the frequentist and Bayesian approach are similar, I think. However, in interpretation, I think if you want to plot the so I'm getting a little bit ahead. So if you want to plot the impulse response of the after you sample or fit the structural var model with some sign restrictions, if you want to plot the sign impulse responses with some confidence band or credible interval in the frequentist world, it's the confidence band have a difficult interpretation. So
yeah,
it is hard to interpret whether. So you can plot it with, say, for one estimate of your coefficients, and then you have many rotational matrices that all satisfy this the sign restrictions you want to impose, and you can plot all those samples of the rotational matrices with your var estimate, and then in this plot you sort of have the confidence band, but this is different from the confidence interval in the frequentist world. But I think in the Bayesian world, if you, for each sample, you find a rotation matrix and then combine this to be a valid draw. And again, for another sample of the var estimates, you find a rotation matrix that satisfies the sign restrictions. And then if you put off all of these draws together, then and you can plot the impulse responses, then I think this has a clearer interpretation in the graphical way. So here it is actually the credible interval or confidence band that you are seeing. So I think that's the one benefit of using the Bayesian approach in this sign restriction methods.
Yeah. Thank you for this explanation. Maybe one more question. So this rotation matrix is different for different sample.
Yes.
From posterior, yeah. So, but we only look for one rotation matrix for each sample, which satisfies the, let's say, restrictions, yes, we impose.
Yeah. Yes, you're right.
Yeah. Okay, thank you.
Yeah.
Great.
Thanks. All right, nice. So many people have the correct numbers, and it is very close to the true structural matrix that we are simulated from. All right, so we can continue to the next part. So other than imposing restrictions on the structural matrix B, we can also impose restrictions on the impulse response functions, and which I just talked about, but I haven't defined yet. So there's nothing stopping us from imposing the restrictions on the B inverse or B0 matrix. So previously we were imposing restrictions on B, so we can now impose restrictions on B0 or B inverse. So B0 is the impulse response function at horizon 0 and why? The reason is because if you look at this equation, so yt is equal to axt plus B0 ut. And if you look at the bottom part here, so you can imagine this is the B0 matrix and this is the ut vector. And this entry will tell us how the first element in ut affect the first variable, because if you multiply these two matrices, this element will get multiplied by this element, and similarly this element will be multiplied by this element. Therefore, this matrix contains how the variables will tell us how the variables will change if the errors ut change. And so we were talking about the first row here, or the first equation here. This is also true for the second equation, or the second row here. And for example, this element will capture how the first variable affect the first shock affect the second variable. And for example, this element will capture how the third shock will affect the third variable, etc. So you can see indeed this B0 matrix will tell us how the variables will respond to the structural shocks. Therefore, we give this matrix B the name impulse response function. And particularly this is for impulse responses at horizon 0. And we can also extend this to further horizons. So for example, we can impose restrictions on A1 B0 to place some restriction at the impulse response at horizon 1. You can do some algebra here to see that. For example, the first equation we can begin from yt plus 1 is equal to a1 yt, a2 yt minus 1, etc. But we don't really care for now. And we can expand yt here to be axt plus b0 ut and plus something we don't really care for now. And then we can collect the terms that or extract the terms that include the structural shocks, the UT that we are interested in. So here we have A1 multiplied by B0 and UT. So you can see this matrix in front of UT will be the impulse response, or will capture the impulse response at horizon 1, because on the left-hand side of the equation, we have YT plus 1 here. Therefore, the entries in this square matrix A1 multiplying B0 will capture the impulse responses at horizon 1. So one example how we can impose these sign restrictions on the impulse response functions is that we can consider again the optimism dataset that we use to forecast in exercise 1. So one way we can define something called the optimistic shock is that we can put a positive sign restrictions here. So this says that the optimism shock should have a positive impact on the second variable, which is the stock prices. So this is one possible way to define the optimistic shock. So after imposing, so we can estimate this model with this restriction, and then extract what is defined as the optimism shock here. And besides imposing sign restrictions on structural matrix B and impulse response functions, we can also do something called a narrative restriction. So suppose we have some strong evidence for the history of one particular shock. And in the supply and demand example, maybe we can have a negative supply shock or an unfavorable supply shock at the beginning of the COVID period. So maybe in 2020 Q1, we have a negative supply shock because we are in lockdown and all the factories are closing. So we have a negative supply shock. We can have a negative supply shock at the beginning at the COVID-19, and this is we can probably believe this to be true. Therefore, we can actually impose this restriction on the structural shocks itself. So this is different from imposing restrictions on the structural matrix B or the impulse responses. Those are the matrices of the estimates we have. However, here we are actually imposing a restriction on the structural shocks itself. So here in the supply demand example, we can impose a negative supply shock during COVID-19. And a second example can be we can impose a negative optimistic shock at the beginning of the global financial crisis. So this is so a negative optimistic shock will be a pessimistic shock. So the way we can impose this is just to impose the optimism shock in 2007 Q3 to be negative. So this will impose a negative optimistic shock or a pessimistic shock at the beginning of the global financial crisis. And there are also other types of the narrative restriction that you can have a look online. But in this workshop, we will focus on this type of narrative restriction that is simply focusing on the sign of the history of a structural shock. And finally, the last type of in the sign restriction class is called the sign and zero restriction. So previously we have introduced the lower triangular identification strategy by imposing m multiplied by m-1/2 zero restrictions will help us to identify the structural matrix B. However, imposing this many zero restrictions, as I mentioned before, can be very controversial. So however, still imposing zero restrictions is a very helpful way to sharpen the inference. So we might want to impose just a few zeros and also some signs on the impulse response functions. And this can be also done in this package or in this methodology. So for example, we can also again consider the optimism dataset. So here, additionally, we can impose this zero restriction here that says, so we change the definition of the optimistic shock from the previous slide to by having this additional assumption here. So this says in addition to having a positive impact on the stock prices, a optimistic shock should also have no effect on positivity, which is a very intuitive way to define a optimistic shock, I think, because just being more optimistic shouldn't increase your positivity, but that should increase the stock prices. All right, so after imposing all those restrictions, we can show something called the impulse response functions. And since these are the impulse response functions of the structural shocks, so these have the interpretation of a dynamic causal effects. And this can be easily done using the package. So if we, after estimating the structural variable model and restricting the sign restrictions, we can plot these impulse response functions. And since we only impose the restrictions on the first shock, which is the here we define as the optimism shock, so we just need to focus on the first column here. And since other shocks are not identified, so we should only focus on the first column here. And we can see the impulse response from this optimism shock. So if you look at the first variable productivity here, so at horizon 0, it is fixed at 0 by our assumption. So if we go back one slide, so we fix the at horizon 0, we fix the impulse response of productivity to a optimistic shock to be 0, which can be seen here. So this is fixed at 0. And similarly, we fix the impulse response of stock prices to optimistic shock to be positive. This is also showing up in the graph here. However, we didn't impose any restriction on the other three variables, say consumption, real interest rate, and hours work. So the interesting thing here is that we see that the consumption and hours work are rising at the beginning of the shock, but these effects are not significant. And for real interest rate, it's always almost 0. And one spoiler is that if we additionally impose some narrative restriction of the structural shock here, then we can sharpen the inference, and then we can make this plots have more significant order, make the confidence bands narrower, and have a sharper inference. And another thing we can do is that we can also visualize the structural shocks. So here, again, we only identify the first shock, which is the optimistic shock. So a history of the structural shocks, we can visualize the history of the optimistic shock. It looks something like this. And here, if you focus on this time point here, this will be 2007 Q3. So this will be the beginning of the global financial crisis. So you can see the mean prediction of the structural shock have a negative value, but the confidence band covers both positive and negative numbers. All right, this brings us to the third exercise. So now we can open the exercise 3.r file, and then we will replicate this optimism example. So the goal here is to replicate the previous impulse response function plot here by imposing the restrictions on the impulse response functions. And the way to do this, again, is to use 1 for a positive sign, -1 for a negative sign, and NA for unrestricted, and 0 for a 0 restriction. So the hint here is, again, to look at the previous slide, slide 24 here. So we just need to create this sign restriction matrix here in this slide. So if we go to RStudio again, and then open exercise 3. So you only here you also just need to edit this part within these comments. So you can modify some elements inside this signed IRF matrix, for example, for 3 to be 1, etc. And after doing this, you can again run this whole script and see if you can replicate the impulse response functions. And so the time now is 1:20, and I will again give you 5 minutes. So I will stop you at 1:25. And while you are working on this, I will explain a little bit of this code. So here so first we load the dataset, and then we specify the sign restriction matrix. And then we specify the specification object. We create the specification object, and we pass in the data, the number of flags, and then the sign restriction matrix on the impulse response functions. And here is the slightly tricky part. So here we use some this block of code looks a little bit complicated, but all it does is to disable something called the dummy observation priors. So here, maybe in the future, we should make the package to disable this dummy observation priors by default. But here we need to do this by hand. So to go into this specification object and then the priors, and then setting these dummy observations matrices to be have 0 columns, which means disabling the dummy observation priors. So in principle, this dummy observation priors, the goal of this priors is to increase the forecasting performance and create a more hierarchical structure of the priors. But here, our goal is not increase the performance of forecasting, and the goal is to replicate some other papers. So the goal here is to replicate the optimism dataset, or to apply the optimism dataset and then replicate the impulse response functions. So here we are turning off this dummy observation priors to make our results as close as to some other paper. And next, we just estimate the model and then compute the impulse response functions.
Sorry, Adam, I have another question about identification, because in your notes, there are B and B0 matrix. Yes, so B0 stands in front the fundamental shocks, like here. Yes, so this is on the right-hand side. This is B0. And in your previous exercise, there was B matrix, which stands on the left-hand side of the equation and somehow links the variables, contemporaneous variables, yes? So when you impose sign IRF in R code, you think about B or B0, or it doesn't really matter? Because, yeah, of course, one is the inverse of the other, but yeah, because I'm a bit confused. We impose restriction on B or B0, or can you explain?
Yeah, great question. So when we impose the restrictions on the impulse response functions, we are imposing the restrictions on B0.
Okay.
So this is the B0 matrix. So maybe this can be seen more clearly here.
Yeah.
So B0 is in front of the structural shocks, and B0 have the interpretation of a impulse response function. However, the B matrix was here in another representation, but the B matrix here does not have the interpretation of a impulse response function. And the B0 matrix here have the interpretation of the impulse response function. At horizon 0.
Okay, I see there are different options. This is IRF structural and IRF the different options in our code. Now I see.
Yes.
So can we do it both at the same time?
Yes, you can.
And another question, because you didn't present the code for narrative restriction. I hope we will see some.
Yes.
But I have a question whether we can also impose narrative, sign, and zero restriction together using your...
Yes, in the next exercise.
Okay, I will wait. Thank you.
Yeah. All right. So it is 1:25 now, and I will keep talking. So I hope most people have successfully replicated impulse response functions. And so let's move on to the next exercise, which is what Maria's interested in. So in this exercise, we will additionally impose something called the narrative restriction we just mentioned. So here we will impose the optimism shock is negative at the start of the global financial crisis at 2007 Q4. And the hint is to look at slide 23. So we want to impose this shock to be negative. I think I have a typo here, so maybe this should be 4 to make things consistent. All right. So another thing is that the row 211 is of the data set of the optimism data set will correspond to 2007 Q4, or maybe this should be Q3. I will try that in a minute. And also you can try to look at this, run this line of code in R to see how you should specify a narrative restriction. And again, I will give you 5 minutes. So 1:27 now. I will stop you at 1:32. And I will also open exercise for myself. Okay, let me check whether it is Q3 or Q4. So 211. No, it should be Q3, I think. So there are 2 typos in this slide. So this should be Q3 and Q3. All right, I will also work on this myself. And I can copy the solutions from Tomasz. And having these 3 lines of code will specify the sign and zero restrictions. But in exercise 4, we also want to impose this sign restriction. Also the narrative restriction. So if you take a look at the help file, it will show you how to specify this narration object. So here we create the narrative object using this specify narrative function. And the start of the period, according to the hint, is period 211. And by default, the number of periods is 1, and that's what we want to use, so we don't need to change anything. And the type is S, so S is imposing the narrative restriction on the structural shock itself. And this is also what we want, so we don't need to change it. But this package also supplies other types of narrative restrictions, for example, A and B. So type A and type B restriction on the historical decompositions. But due to the time limit, I won't introduce those in this workshop. Okay, back to how to specify this narrative restriction. And also we want to, however, we want to change this argument here because we want to impose a negative restriction. So we want to set sign to be -1. And yes, we want to impose that with the first shock and no restriction on any variable because we are just focusing on imposing the restriction on the structural shock. So it doesn't depend on any variable. So we will leave it as NA. And I think after this, it will work.
But Adam, if we want to specify the variable that are hit by these shocks, we put it as a vector in var parameter, yes? So like, I don't know, if we assume that it hits only first two variables. Sorry, this is beyond the task, yeah, but I just curious about this VAR parameter inside those narrative restriction specification. Okay, but because we can assume that it's negative and hits specified variables, yes? Am I correct? Yes. Okay, yes. Okay. Okay, I will try later. Okay, thank you. That's my question.
Yeah. So for example, here we can specify that optimism shock have a positive impact on stock prices, and also during the global financial crisis, it is negative. So I guess maybe you can impose other restrictions to building on these examples.
And maybe another question. Of course, most of those restrictions are cannot be tested, yes? Because it's like those restrictions, I think, maybe I'm wrong, does not change the, let's say, marginal probability of data, or they change. I don't know. I have just a question. Yeah, how they change the goodness of fit in Bayesian sense. So I don't know whether you can take.
Good question.
Okay, I will think about that. Probably the sign restriction does not change much, yeah, but maybe those. I'm talking about zero restriction, not the sign, but maybe the other change a bit, yeah, or not. Okay, I will think about that.
Okay, thanks. I think the underlying VAR model is not affected, so the goodness of fit should be the same. But I also remember somewhere in the literature that imposing narrative restriction will change the likelihood. So that might be that also might have effect on the goodness of fit. I'm not too sure.
So then you can test it, yes. If they change your likelihood, they change your probably marginal data density, and then probably you can test it somehow. Okay, never mind. I will think about that later on.
Yeah, that's a very good question. Yeah, I will also think of that. All right. I think we are finishing exercise 4. So here, if we additionally impose this narrative restriction, you can see that the inference become much sharper. So for probably not for real interest rate, it's still non-significant. But for consumption and always work, it is much more significant. So previously, it was the 68% credible interval was covering 0, but now it is significantly different from 0. So you can see the benefit of imposing this narrative restriction is that we can narrow down the credible interval and make our inference sharper. All right, and I assume most people have successfully replicated this exercise. So I will move on to our last section, application in macroeconomics. So according to the Wikipedia, a monetary policy is the policy adopted by the monetary authority. I think in European countries, that's the European Central Bank. In the US, it's the Federal Reserve. And then in Australia, it is the Reserve Bank of Australia. So the monetary authority of addition to affect monetary and other financial conditions to accomplish broader objectives like high employment and price stability, or even low inflation or suitable inflation. So to implement these monetary policies, the central banks can do two things. They can either raise or lower the interest rate, but obviously they can also do other things. But here we are just focusing on how the central banks can manipulate the interest rate to implement monetary policies. So first, the central banks can raise the interest rate. If the interest rate is higher, that will encourage people to save more money in the banks. So that means there will be less money in the market. Therefore, this will mean a contractionary monetary policy because there are less money in the market. So the economy should cool down. And second, the central banks can also lower the interest rate. And this will make people want to put less money in the bank. So that means people are spending more money in the market. So this will be an expansionary monetary policy. So a more intuitive way to think about this is, I think, is to you can consider the economy like a machine or like a car or a computer. So when the economy is having a high inflation or high output, that means the machine is overheating itself. So we want to cool down the machine. And therefore, we can adopt this contractionary monetary policy. And if the economy have a low inflation or low output, that means our economy is underperforming. So we want to heat up the machine or the economy. So here we want to use the expansionary monetary policy. All right. So so obviously the central bank does very complicated things. Here's a simple rule that might capture some aspect of what the central bank does. So this is called the Taylor rule. And this rule is to describe the monetary policy using this equation, which is a very simplified version of the real world, obviously. So the left-hand side is the nominal policy interest rate. So that can be the cash rate in Australia and the federal funds rate in the US. And the right-hand side of the equation will be the natural interest rate plus inflation rate, pi t, and plus some positive coefficient, a pi, multiplying the gap between the inflation and the inflation target, and plus, again, a positive coefficient, multiplying the gap between GDP and potential GDP. So all these are natural interest rate, inflation target, and potential GDP. So the words natural and target and potential just means that's the target or the goal we want to achieve, and that's the best we want to have. So as long as inflation is deviating from the target, we want to adjust according to this equation. And also if our output is different from the potential GDP, then we want to adjust according to this rule. So what this rule says is that we want to raise the interest rate. That means we want to cool down the machine or the economy when the inflation or output is too high. And we also want to lower the interest rate. That means to heat up the machine or the economy when inflation or output is too low. So usually there's some form of the Taylor rule in a structural bar model when we want to analyze the monetary policy shock. So usually we will want to include variables like the interest rate, inflation, and GDP. So to have some kind of Taylor rule in the equations. Okay, so to fix ideas, we can consider an Australian example because I'm in a Australian university. So let's consider an Australian example. So the question we want to ask is, so previously we say that raising interest rate is cooling down the economy. So that's like a contractionary monetary policy. But is this really true? So we want to answer this question. Is raising interest rate really contractionary? And we can do this by analyzing a positive monetary policy shock. So a positive monetary policy shock will raise the interest rate because by definition it's positive. So it will increase the number or increase the variable on the left-hand side. So we want to analyze the effect of a positive monetary policy shock and see whether it is actually contractionary or expansionary. And here we include, we have 4 variables from 1982 Q1 to 2019 Q4 using these 4 variables. So as I mentioned in the previous slides, we want to include these 3 variables to have some kind of a Taylor rule in the model. So we have the interest rate or the cash rate, which is the policy interest rate in Australia. And second, we have the GDP, the real gross domestic product, and also the CPI, the Consumer Price Index. And it can be used as a measure of inflation because if CPI is increasing, that means we have a positive inflation, and if CPI is decreasing, we have a negative inflation. Sorry, if CPI is lower, that means the inflation is dropping down. And the last variable is something called the trade-weighted exchange rate. So this is defined as the exchange rate when this number is higher, that means the domestic currency. In this case, the Australian dollars is stronger. So we can read this dataset, and this is a preview of the dataset. And actually, if you run the command head data set in R, you will see some other variables, but those are the exogenous variables from the US economy. So I'm not showing them here. So here we only consider these important 4 endogenous variables. And this is an example taken from this paper. All right, so here we want to impose some restrictions on the contemporaneous relations or the structural matrix B. So here we just want to identify the first shock and then name it as or define it as the monetary policy shock. And the first thing we can do is put some restrictions on the B matrix here. So if you look at the first row of this equation, we have B11 multiplying cash, B12 multiplying GDP, B13 multiplying CPI, B14 multiplying TWI is equal to some all the lag terms and plus this UTMP, the monetary policy shock. And we can again move this B12 GDP to the right-hand side. So we have negative B12 GDP. And similarly, we have negative B13 CPI and negative B14 TWI. So based on our previous discussion, so if the central bank want to impose some kind of the Taylor rule, then the following some restrictions should be satisfied. First, to make our life easier, we just normalize this B11 to be positive. And then we want to make B12 negative, so that a negative sign multiplying B12 will be a positive number. That means when we have a very high GDP, then we want to increase our cash rate to cool down the economy. And similarly, if the inflation or the consumer price index is increasing, then we again want to assign this coefficient to be negative. So together, this is a positive coefficient. And that means if inflation is high, then we want to also cool down the economy. And lastly, for the exchange rate here, we want to impose it to be positive, so that negative multiplying positive will be negative. So that means when the exchange rate is too high, then we want to discourage people from investing in Australian dollars anymore. Because if the exchange rate is too high, that can also have some bad effects. So we want to restricting the exchange rate to be going too high. All right, so we can impose this Taylor rule type restriction on the structural matrix B here using these signs. So B11 positive, B12 negative, B13 negative, and B14 positive. So you can already see that after doing the exercise, we just need to change the sign of the first row of the matrix B here. And then in addition, we can also impose some restrictions on the impulse response functions. So because restricting on B is not enough to identify the monetary policy shock, so let's consider some restriction on the impulse response functions. So let's think about the question: what happens when what happens to the variables? These four variables when we have a positive monetary policy shock. So first, by definition, if we have a positive monetary policy shock, then the cash rate should increase, or the policy interest rate should increase. And second, we don't want to restrict anything on the impulse response of GDP, because that's the thing we want to analyze or see how GDP responds to a positive monetary policy shock, so that we can determine whether a positive monetary policy shock is indeed contractionary or expansionary. And third, we want to impose a negative sign for the consumer price index. So we expect a negative inflation after having a positive monetary policy shock. Or we should expect inflation to drop when we have a positive monetary policy shock. And lastly, we want to also restrict that the exchange rate to increase when we have a positive monetary policy shock, because if the interest rate increases, then we should expect the exchange rate to be higher, because people are investing. This encourages people to invest in or save or to hold Australian dollars. And clearly, we can also extend these restrictions to not only on the first horizon or the horizon 0. So we can also extend this to further horizons like horizon 1, 2, and 3. So in the spoiler, so in the paper we want to replicate, we actually restrict this to horizons 0, 1, 2, and 3. But you only need to create the encode. You just need to create this matrix once, and then you can replicate that matrix to a 3-dimensional array to impose this restriction to further horizons. And here's the result if you run the code. So for cash rate, we see a positive response, that's by definition. And also we see a negative response from the consumer price index, that's also by our construction from the restricting the impulse responses. And also we see a positive response of the exchange rate, that's also by our construction. So the only interesting here is what happens to the real GDP. Because we didn't impose any restriction here, so we can see that here real GDP have a drop, or a significant drop after a positive monetary policy shock. So this can confirm our hypothesis that a positive monetary policy shock is indeed contractionary, because it's lowering the real GDP in the upcoming future. And this is 20 periods, and we have quarterly data, so this will be about 5 years. All right, so this brings us to the last exercise, which is exercise 5. So in this exercise, we will just analyze what we talk about, the Australian monetary policy dataset. And then, so the goal is to replicate the impulse response function plot I just showed you. So, and also the way to do this is that just use the restrictions I just showed you from slide 33 and 34. So we need to impose first restrictions on the structural matrix B, and then also the restrictions on the impulse response functions. And again, we use 1 for positive sign and -1 for a negative sign, and NA for an unrestricted sign. So if you go to slide 33, you will see this the hint how you should impose these restrictions, and also slide 34, you will see how to impose the restrictions on the impulse response functions. All right, so it is 51 now. So again, I will give you 5 minutes. So I will stop you at 56. And I will also open our studio myself. So while you are working on this example exercise, I will also talk through the code. So here I used this additional package that maybe some of you haven't installed yet. So maybe you should install the packages with Excel first. And after doing that, you can load this Excel file. So after loading this Excel file, we just log transform the data. And then we assign the endogenous variables as the second to the 5th column. So that will be the 4 variables we just discussed. So cash rate, CPI, etc. And we also want to specify these exogenous variables from the US economy. And this slightly complicated code is just doing the transformation of creating the lag values of the exogenous variables. And then similarly as before, we just need to edit this part within the comments to replicate this Australian monetary policy example. So you just need to manipulate the sign structure here, matrix here, and also the sign impulse response function matrix here. And after doing this, you can see this line of code will replicate the sign impulse response functions to 4 periods. So this will replicate this matrix to a 4x4x4 array. And this will help us to impose the restrictions to a total of 4 horizons. And as before, we will specify the model using this function. And then we also, again, using this slightly complicated code to disable the dummy observation priors. And finally, we sample from the posterior and then compute the impulse response functions and then plot the results. So again, we just need to edit this part within the comments. And according to the slides, we want to impose B1 to be positive and then B1 to negative, negative, positive. So maybe we can do this. So the first row would be equal to positive, negative, negative, positive, negative, and positive. And for the impulse response functions, we want to impose the first column to be positive and a negative positive. Positive and a negative and positive. And hopefully this will work. Yep.
Adam, I just want to ask a question about row 26, because you tried to replicate your sign restriction also for the other horizon, as I understand. Yes, so the same restriction for horizon 1, 2, up to 4. Yes,
Yep.
26.
So
Okay.
if
Okay.
you
Yeah, of course, it depends on your assumption. Yes, whether it maybe it's too restrictive. Okay, but okay, I understand. So you did it in 26. Yes. Okay.
yeah. All right, it is 56 now, so I will keep talking. So as I shown you here, so if you modify these two matrices and then run the code, it will replicate the impulse response functions as I have in the slides, and we see this have a drop in the real GDP after a positive monetary policy shock, which matches with our hypothesis that it is have a contractionary effect. Yep, and here's the result. So that concludes this workshop today, and you can go to the bsparse.org to look at a package or many packages that created by this bsparse organization, which includes obviously includes bsparse science, and this is our GitHub link. And you can also contact us through email using this email link. And you can also find us on social media, Fosodon, using this user. And also we are also on Blue Sky. You can find us with this username. And we also have a logo for the organization. And yep, thank you for coming today. And if you have any questions, just unmute yourself and or type in the chat. And you can, or if you have questions in the future, you can send me an email at this email address. And we can be friends on LinkedIn, GitHub, and also Blue Sky. And yeah, that's all for today.
Thanks a lot, Adam, and yeah, thanks to everyone who attended. So yeah, I think we could wait for like maybe 1 more minute to see if anyone has questions, and if not, I think we can end it here. Thank you again.
I have a quick question, if you don't mind. Can you hear me?
Yep, okay.
Regarding Minnesota prior, the setting the value of a parameter equal to 1 for non-stationary variables apply only to variables only with 1 unit root, or it can be also assumed for variables integrated of higher order, like E2 variables or...
Yes, I guess you can also, for I2 variables, you can also set the intermediate sorted prior to set it equal to 1.
Okay, so if I recall correctly, it is also suitable for a higher degree, for example, E2 or E3. In each cases, no matter of degree of integrated, I can set 1. Yes?
To be honest, I'm not too sure of this answer.
Okay.
Yeah, so I'm not sure if it is integrated of order 2, whether setting in this A underscore matrix an element to be 1 is whether this is suitable for some variable that is integrated of higher orders.
And just one comment. Actually, probably those SVR are good models for stationary time series. So, and maybe they also works for some non-stationary time series. And my question is quite connected with the previous one. So, are there any chances for extending it for co-integration relationships somehow? Because how you deal with no stationary time series? Yeah, because yeah, basically we can see non-converging to zero impulse responses. These are the, let's say, let's say that these are the proofs that we can deal with no stationary data. So my question is how to deal with no stationary time series in your approach. It is somehow possible to take care of non-stationary time series, or should we transpose those series to stationary by, I don't know, taking the difference of or other transformation?
So for at least for integrated of order 1 non-stationary variables, in the Bayesian approach, we can actually just apply the structural var as it is, so we don't need to transform the variables. And you can see in this optimism data set, in fact, the most of the variables are, for example, the first variable is clearly non-stationary. So, and the third variable is also clearly non-stationary. So as long as we set the correct Minnesota prior, so putting once in the correct entries, then we can estimate the model without much problem, and we don't need to transform the variables, say differencing, before estimating the model. And this is proved in a paper that I think in the frequentist world, if the variable is non-stationary, then it will follow some, in the limit distribution will be some Brownian motion, but in the Bayesian world, still we don't need to worry about that limiting distribution.
So you are not assuming that they co-integrate somehow, yes? It is not necessary to assume that those no stationary variable, a linear combination of them co-integrate, so it's stationary to have a I don't know, consistent estimator. Okay, I will read about that. Thank you for that comment. But
yeah, I think I'm not familiar with the combining co-integrated variables and structural var, but I guess there should be literature on that in that area, because this seems to be a very connected topics.
okay, and maybe do you test the roots of characteristic polynomials somehow to test whether your VAR is stable? Maybe the last question, I don't want to extend and to take too much time. It is not inside probably it is included in your code to check whether you have a stable VAR model or
We don't really at least in the code we provided in the exercises, we don't actually test for stationarity using the characteristic roots because in the Bayesian world we don't really need to worry that much about non-stationarity.
Okay, so thank you for really inspiring and detailed presentation. Thank you very much.
And thank you for the questions and also coming today.
Thank you. Goodbye.
Thank you.
Yeah, thank you again to everyone from me and especially to Adam. So yeah, I think we can end it here. Thanks again, and have a good rest of your day. Bye.
Thank you. See you.
Thank you. Bye bye.